All right. Definition 211. Two events, A and B, are said to be independent. If and only if. If and only if. IFF is formal. This is if and only if. That is short for if and only if. IFF. If and only if the probability of B given A is equal to the probability of B. That is the conditional probability of an event B given another event A has occurred is just the probability of B. Or similarly, vice versa, if you have probability of A given B is just the probability of A. That is, B occurring first has no impact on whether or not A is likely to occur. They are independent. Otherwise, events are dependent. Otherwise, we would say A and B are dependent. So, independent events is this definition based on conditional probability relationships. Not to be confused with events that are mutually exclusive or disjoint. Independence is strictly based off of these relationships, okay? All right. So, let's dive into an example here. And let's consider flipping two coins. Flipping two coins. Let's just say we have a coin A and a coin B. Flipping two coins. If it is known that B comes up heads, what is the probability that A is also heads? If it is known that B came up heads, what is the probability that A is also heads? So you might be able to go to your piggy bank, go to your coin jar, grab two coins, right? Call one of them A, call one of them B. You flip them. B comes up heads. What's the probability that A comes up heads, okay? Well, let's just take a look at this. What's our sample space here, S? Our total sample space. Well, you could have A can come up heads and B can come up heads. We could have a heads and tails for A and B. A could be tails, B could be heads. A and B could both come up tails. All right. And so let's use this. So let's see here. What do we know? What is the probability that A is equal to heads? Well, there are two events that would correspond to that out of the 4. 2 out of 4 or 1/2, right? 2 out of 4 or 1/2. What is the probability that the coin B comes up heads? Well, that would be these last two, here and here. So also 2 out of 4, also 1/2. Although two different events out of the 4, still 1/2. Still 1/2. The last thing I'm going to have us look at are what's the probability that A and B are heads? Probability that A and B are heads. Well, that's only this one event right there. So that is a 1 out of 4 shot. That is a 1 out of 4 shot. Okay, so now to the main course. What's the probability that A is also heads given B came up heads, right? The question is, if it's known that B came up heads, what is the probability that A is heads? Probability that A is heads given B is heads. Well, according to the conditional probability definition, this is the probability of the intersection, A and B equals heads, divided by the probability of the given. Divided by the probability of the given event. And so what's the probability of the intersection there? That's 1/4. What's the probability that B comes up heads? We know that to be 1/2. And so the desired probability then is 1/4 over 1/2. 1/4 out of 1/2 is 1/2. Is 1/2. Notice that's the same as the probability that A is heads. So the probability that A is heads given B is heads is the same as probability that A is heads. This means they are independent. Independent. They are independent, which is kind of obvious, but maybe not necessarily, right? If you take two coins in your hand and you flip them simultaneously, if they're, just whatever, both quarters, the fact that 1/4 comes up heads should have no impact on the likelihood the other quarter comes up heads. Those are independent events. This is we just shown in a long-winded way mathematically with probability numbers that is in fact the case. Those are independent events, okay? Let's take a look at another example. Let's say we know some things here. We're given that the probability A is 0.7. The probability of B is 0.1. And the probability of C is 0.05. The probability of A intersect C is what? 0.035. And the probability of B intersect C is 0.03. Okay. So the question is C independent of events A and B? Independent of events A and B? Is C independent of A and B? Well, let's take a look. We know the probability of C is 0.05. So if the probability of C given A is 0.05, then we know they're independent. Well, according to the conditional probability definition, this is the probability of the intersection of the events divided by the probability of the given. So the intersection there is 0.035, given in the problem, divided by the probability of A is 0.7. So 0.35 divided by 0.7. Run that through a calculator, just double checking. That is in fact 0.05, which is the probability of C. There we go. So A and C are independent. A and C are independent. I guess I should start writing that out there. Independent. A and C are independent. How about B and C? Let's take a look. Probability of C given B is the probability of the intersection divided by the probability of the given. This intersection is 0.03 now, divided by the probability of B, which is 0.01. Not 0.01, 0.1. So that's 0.1. So 0.03 divided by 0.1, that is 30%, or 0.3, which is not equal to the 5 that we want, the 5%. That is not equal to the probability of C, and that's all we need then to say that they are dependent. This would mean B and C are dependent. B and C are dependent. All right, so just a little bit of basics there on independence, okay? Now, one thing we commonly do here is manipulate this relationship between the conditional probability And this ratio of probabilities, the ratio of the intersection probability and the probability of the given event. Theorem 210 says, basically, after we understand what conditional probability is, we have another way to compute the probability of the intersection of two events, and that is just the probability of A times the probability of B given A. This is called the multiplicative rule. This is called the multiplicative rule. Multiplicative rule. Close that off. Multiplicative rule, right? And what this really just sort of comes from is basically comes from the idea that probability of B given A is defined to be the probability of the intersection divided by the probability of the given. And so we can just multiply this over to the other side, right? We can multiply that over to the other side. Okay, which is nice. Now, actually, something that's worth noting here, also note that because the probability of A intersect B is equal to the probability of B intersect A, in the multiplicative rule relationship, you can basically change what you're conditioning on in either fashion, right? Since these are equal, this can also be thought of as the probability of B times the probability of A given B. Or the probability of A times the probability of B given A. Either way you want to think of it, that is how we can help make it shake down a little bit, okay? Multiplicative rule. Let's do an example here with the multiplicative rule kind of coming into play, all right? Let's say we have one bag that contains 4 white balls and 3 black. 4 white. We got 4 white balls and 3 black. 3 black balls. And there's a second bag. A second bag contains 3 white and 5 black. Second bag contains 3 white and 5 black. Okay, so here's the scenario. One ball is drawn from the first bag. One ball is drawn from the first bag. And placed unseen in the second bag. Placed unseen in the second bag. So we draw one and we put it in the second bag where we're not looking at what that is. So this question is saying, what is the probability then? What is the probability that a ball now drawn from the second bag is black? What is the probability that a ball now drawn from a second bag is black? All right. Well, let's take a look at this. This is a 2-stage problem, and when I can clearly define stages there, I think tree diagram. So let's go ahead and maybe try to tackle this with a tree diagram here. Tree diagram. Okay. So first we have what's going on in bag 1. And then we're going to have something going on and we'll be drawing from bag 2. But first we draw from bag 1 a ball that is unseen, right? So in bag 1, you have 4 white and 3 black balls, okay? Now, you can either draw a black ball and put it in bag 2, or you can draw a white ball. So let's say this branch will be for drawing a black ball, moving it into bag 2, and this branch will be for drawing a white ball, moving it into bag 2. All right? What's the probability that we draw a black ball in bag 1? Well, there are 3 black balls and 4 white, so there's 7 total. That probability is 3/7. So I'm just going to put that on the branch there. Probability that we would draw a white ball, move it over to bag 2, then would be 4/7. Now looking at bag 2, you have 2 cases to consider. If we're on this first branch and we've drawn a black ball and put it in bag 2, bag 2 initially has 3 white and 5 black, but we've drawn a black ball and put it into bag 2. So bag 2 now contains 3 white and 6 black. 3 white and 6 black, all right? So what then is the probability of drawing a black ball from this bag? Well, there are 6 black, 3 white. That is 6/9. 6/9, okay? 6/9. Think about what this is here, right? Think about what's going on here, okay? This is the probability of the first ball being black from bag 1. So I'm going to say that's like B/1 or something like that, right? This 6/9 is a conditional probability. Given that you had a black ball from bag 1, what's the probability you get a black ball in bag 2? That's a conditional probability. Multiplying these things together would give us the probability that we get a black ball in bag 1 and a black ball in bag 2. 3/7 times 6/9 is what? 2/7. 3/7 times 6/9 is 2/7. That's the probability that we got a black ball in bag 1 and then a black ball in bag 2 here. That's an intersector probability. That's exactly the multiplicative rule, right? The multiplicative rule, this right here, the probability of the intersection being the probability of the first event times the probability of the second given the first, is giving us a reason or a true explanation on why, when we move down the branches of these trees here, that we are multiplying these probabilities out. Because this branch, the end of this branch, corresponds to this intersection. How can one compute the intersection? This probability times this probability via the multiplication rule. All right. Now, of course, in this scenario, we have 2 disjoint cases, getting a black ball first or a white ball first. So let's just finish this one out. If we got a white ball first, what does the second bag contain? Originally 3 white and 5 black. This would now be 4 white and 5 black. And so then the probability of getting a black ball here would be 5/9. 5/9. And so again, looking at this is the probability of getting a white ball in the first case. This would be the probability of getting a black ball in the second, given we've gotten a white ball first. And we're looking at the probability that we have gotten a white ball first and a black ball second is 4/7 times 5/9. 4/7 times 5/9. And so what is that? We'll add this together here. But it doesn't look like that reduces down too much. So 4 times 5 is 20. Over 63. 20 over 63. Okay. So what is the probability we get a black ball drawn from the second bag? Adding these up in these 2 disjoint cases, that would be probability of getting a second ball black after moving 1 from first bag would be 2/7 plus 20/63. And that is common denominator is 63 there. 18, that'd be 38 63rds. 38 63rds. All right. Okay, that's enough for now. Time for another break. Let's go ahead and grab a drink, grab a snack, and come back. We've got one more video probably to go here before we finish up our discussion on conditional probability and independent events. We will see you in a bit.